my pleasure and honor to introduce Dr. Lina Kattan. Lina is a graduate of UT-ITE, right here in this room. I won't say when, that was some time ago. And she moved in to be a star. So Lina, more formally, is a celebrated figure in civil engineering from the Schulich School of Engineering, University of Calgary. She is the current director of the NSERC CREATE program in integrated infrastructure for sustainable cities. She's also a member of the College of Scholars, Artists and Scientists of the Royal Society of Canada. She has received many accolades, including the 2014 Killam Engineering Research Leader Award in NSERC category. Today, Lina will share with us some of her work, a presentation titled A Data-Driven Approach to Network Analysis, Case of Non-Recurrent Congestion. So Lina, without further ado, the floor is yours.
Thank you. Thanks a lot for the introduction and good afternoon, everyone. This place really holds such a special place in my heart. I don't believe I would have been here without the support and the education I have got from University of Toronto. And so I'm a little bit nervous, by the way, just like want to confess. When I took the go in the morning and came to campus, I felt like as if I'm coming to defend my thesis again. So I changed a little bit the title and added prediction. I saw Bahir in during the weekend, and I felt I need to make him happy and add some machine learning research. Okay, so today the transportation community is passing through an exciting time because we are able to track almost everything happening in our network. So if a link is disrupted due to collision or extreme event, the impact is not only felt on the intersection itself, on the link itself, but also propagates through time and space in the network. And it's very important to understand how this congestion is building up and how it's shrinking in order to be able to conduct vulnerability analysis and resilience analysis of our network. So this is the focus of my talk, and I'm going to mainly focus on data-driven approaches. So that would work. That's okay. Okay, so this is the outline of what I'm going to go through. So as we know, transportation systems are the blood vessels of our communities. They connect us to our families, our institution, and really our life. And with more congestion, we have more pressure on our transportation network, and we have deterioration in the network performance. And also the challenge, we have growing challenges in having access to sustainable, reliable, and efficient services, goods, and opportunities. Disruptions are inevitable, and especially with today's climate, we have more climate change and more extreme events, which are really hitting our network and impacting the performance of our transportation network. And things are going to be more challenging when we have a dense urban network because of the non-linearity of congestion and the non-linearity between demand and supply. And travel behavior adds to the complexity because at the end of the day, congestion is the result of many players and many travelers deciding where to go, when to travel, and where to travel. And real-time information can also add more to the challenges we have. It can also produce the information paradox, so meaning sometimes when you give more information, you have more deterioration in the performance of your network. So it's very important to identify the vulnerable links in your network in order to inform policies to increase the resilience of your network. So today, we have often access to multi-years data, historical data. And this historical data can be reconstructed and can be analyzed to reconstruct how congestion is building up in the network and how it's shrinking, so we can reconstruct the response time on the network level. So most of the research is dealing not with a freeway network or an arterial, with the grid network, because things are much more challenging in a grid network. So I'm going to give some insights from 4 data-driven research. So I will start with the first one. So in this research, we built a generalized extreme value distribution in order to model extreme events. So empirically, it's known that the relationship between travel time and standard deviation follows a linear relationship. So this means as the travel time increases on a lane, the variance of this travel time also increases. So we're interested to see, and most of the time whenever they have extreme events, so they treat it as outliers, and this data is disregarded from the studies, from the analysis. So in our research, we're really interested mainly in looking at these extreme events, and we want to see if also we have a linear relationship between the extreme travel delays, travel time, and also their standard deviation. And once we establish this linear relationship, we can model the extreme travel time. So the first step is to, so we have access to data, we have access to 6 years data from the city of Calgary. And the data is updated every minute, and it covers 85% of our transportation network in the city. And so we have information on the time of observation, average travel time, average speed, link length, and for sure, the data also includes information on extreme delays. So the first step is to be able to isolate these extreme events. So there are many methods to do that, and we use the blocking maximum method. So basically, you divide the data into blocks, and for each block, you take the extreme observation. And then you take the average, so you take the mean, and you can measure the standard deviation of these extreme observations. So this is what we did, so this is an example for a one-day block, but our block was a 1 week block and 1 month time interval. And we did the data for all the links that we summarized that, like for all the links that we have observation, extreme travel time observation for. So we ended up, because we have 6 years of data, we ended up for every single link to have 72 observations related to monthly observation. And then we did it by season. We have 24 observations for the 6 years. And indeed, the data showed some linearity with the relationship passing through the origin. So this means when the delays is 0, the standard deviation is also 0. But if you observe here, the data also exhibits some heteroscedasticity. So this means the higher the travel time, not only the higher variation, the higher standard deviation, but also the higher is the variation within the standard deviation. So this means if you take the same observed, so this is an example for one link in Calgary, but we have the similar behavior for all the links that we study. So this means for the same delay, you can have cases of more or less homogeneous traffic and cases of heterogeneous traffic. And heterogeneous traffic is most of the time related to gridlogs. So remember, we are mainly dealing with the right side of the fundamental diagram because we are dealing with extreme events and extreme delays. So we know that the data is going to exhibit some stochasticity. So the heteroscedasticity tells us that we don't have an additive error term, we have a multiplicative error term. So now we can come with a compounded generalized extreme value distribution in order to model the extreme travel delays. So this is the form of the compounded generalized extreme value distribution that we have calibrated. So it's compounded because it tries to model the seasonal variation and the month-to-month variation. So maybe you can understand what I'm trying to do here. So we have the time interval, we have the block interval, and then we isolate the extreme and the extreme events, and we can get the distribution of the extreme event, and then we have it by season. And so we try to get a distribution that characterizes both the month-to-month variation in travel delays and also the seasonal variation in travel delays. So in order to validate our results, we also compared the model to the model that doesn't have a compounded generalized value distribution, just like one distribution for monthly variation and another one for the seasonal variation. And we tried the model on for 4 different seasons. And so this is an example again for the same link on Shiganapi. And you can see that the compounded generalized extreme value distribution fits the data much better, because it's able to model the variation, the seasonal variation and the monthly variation. And the same patterns and the same results, we got the same results for all the other links that we examined in the network. So the next step is to come with the vulnerability index. So the vulnerability index that we come with is the product of the return level of extreme delays times the importance of the link. So the return level is the probability of one maximum travel time delay being exceeded in a given season. So it was a seasonal return level that we adopted. And the importance of the link is solved using this optimization problem that tries to find the contribution of every link towards the overall network performance. So the more the link is contributing to network performance, this means it plays an more important role in the network. So by doing this product, we can come with the vulnerability index, and then we can rank the links in the network, and we can spot the important and the vulnerable links. So these are the results that we got. So we have a cluster. So this is zooming a little bit more on downtown Calgary. So you can see downtown Calgary. The results showed us that the links are very vulnerable, and this makes sense because we have all one-way streets. So whenever an accident happens, there are lots of detours going on. So they're limited route choice behavior. And also we have another cluster is on 16th Avenue, which is the Highway 401, the same as 401, the Trans-Canada Highway. So we have a very high demand, but at the same time, we don't have much density of streets, so not much redundancy in the network. So this is the first study. And the second study, we got also access to accident data, to collision data. So we thought like maybe we can combine both database and to reveal more information about the probability of collisions and how it affects vulnerability, network vulnerability. So the collision data, we have it through the city of Calgary by type of incidents, time, location, occurrence time, clearance time, and the severity. The severity is just the number of links that are blocked for the given incident. And again, we have the index data. So what we're trying to do here, so again, whenever we have a collision happening on one link in the network, the travel time is going to be deteriorated not only for the link itself, but because we're dealing with an urban network, the travel time is going to be changed also on the neighboring links, but it's going to change differently. So for instance, if you have blue here, the distribution of travel time when you don't have an accident or any collision, and if we can calibrate another curve when we have disruptions. So when we have disruptions, we assume that links that are affected are going to shift from the blue curve to the red curve. So this is what we're trying to see in order to get a spatial analysis. And then if you do it by time, we can get a spatial temporal analysis of how congestion is building up. And also we can do it when the congestion also is shrinking, to see also how the network is absorbing and when the network is absorbing the collision. So the methodology that we came with consists of two steps, a spatial impact analysis and a temporal impact analysis. So for the first step, we calibrate the travel time under normal condition. So because we have access to both database, we can isolate the travel time that don't correspond to incidence, and we have the one that correspond to incidence, and we can calibrate both curves. And then by conducting hypothesis testing, we can see how much deviation, if we have statistically significant deviation in travel time because of a collision. And this way we can identify the spatial impact of the collision. And we do it by time. So if we do it by time, as we're going to do in the next step, we can also identify when it's going to disappear and when the collision, the impact of the collision is going to be absorbed by the network. So in order to do that, we use a normalized mutual information index to identify the similarity between traffic patterns of consecutive time interval and also on neighboring links. So this is an example of how this works. So we have an accident that is reported to take place on Macro Trail in downtown Calgary. And the accident is reported to occur at 9:05 and reported to be cleared. So they just removed the accident from the network at 10:40. So by building the spatial temporal analysis, you can see that you can spot some congestion even before the accident happened, reported to happen. So it might have happened before, but it's not reported till 9:05. So the way we do it by looking at the NMI, and anytime we have a sudden drop in the NMI, we know there's a dissimilarity in traffic patterns, so something changed in the network. So we can identify this is when luckily the accident happened, and this is when the accident is being, the effect of the accident is cleared, not the accident being cleared, because you can remove the incident, but because of shockwave theory, the impact can still propagate in your network. So the flow recovery time is when the impact of the accident is being absorbed by the network. And so we did that for all the collisions we have. And so this is, so most of the time, the occurrence time is very close to the reported time, but the clearance time, it's expected to be more than the reported clearance time, because we're not reporting the same thing, because they're reporting only when the accident is removed from the network, but we're reporting when the accident is being, the impact of the accident is being removed. So it's two different things. So now we thought we can update our vulnerability index by adding the impact of the collision and the consequences of the impact on not only the links that are impacted by the accident, but also on the unmediated links. So we have the impact on the mediated links, the one that is subject to the accident, and the one that are not subject to the incident. And so we repeated the analysis, and we got similar results in downtown than the earlier study. However, this study also revealed other corridors that were also very vulnerable, but very vulnerable because the block maximum method only spots the maximum extreme event per week, but on Deerfoot, it's very well known we might have an accident every day. So it spotted, for instance, Deerfoot to be a vulnerable corridor, and also Crowchild and Glenmore. So these are the corridors that are more prone to congestions because of accidents. Okay, so this is the third study. It's more resilience. So the two first studies are related to vulnerability analysis. This one to resilience, and this is accepted in the NICE International Symposium on Transport Network Resilience in Hong Kong. And it's based on the work of my master's students, USB. So this is the resilience triangle. So in the resilience triangle, we have the time, and then a disruption takes place in the network, and then you have drop in your network performance. And when the network performance drops to the maximum point, you can measure how vulnerable is your network. And then with time, if you remove the accident, the performance of the network is going to go back to normal, right? So this is the theoretical one. And then it will go, more and this is the theoretical one, but in real life we have stochasticity even in the performance, so you have fluctuation even in the performance of your network. So what we're trying to do, using the data that we have, again, the incident data and the index data, we want to reconstruct this triangle. So there's something very important about resilience analysis. You might end up having the same resilience level, but for two different reasons. Because it has a performance dimension, and it has a time response dimension. So you might have low resilience because the link is very vulnerable, but very fast to recover for some reason. Or you might get a link that is not vulnerable, but it's very, very slow to recover. So it's very important to understand these two dimensions of resilience analysis. So again, we use the combination of the same database, and this is the overview of the methodology. It has a recovery time determination step and a link resilience matrix step. So in the first step, it's very similar to what we did in the previous paper. We combined the two databases, and then we constructed the distribution of travel time per day of week and per time period. And then we did a hypothesis testing whenever we are studying the accident taking place on one link in order to spot and to identify the spatial impact. And then by tracking the spatial impact and so we're doing hypothesis testing for every time step. So whenever the hypothesis testing is showing us there's no more difference in the travel time, this means the impact of the collision on this link is being removed, and so on. So we can determine when the recovery time takes place. And then, so what we did, this step is somehow borrowed from complex network science. So what we did, we constructed an origin destination table for downtown. So all the analysis mainly focusing on downtown Calgary. And so we did the origin destination travel time matrices during normal time for every day of week and time of day. And we did, whenever we have an accident, we built another matrix using the shortest path. And then we determined the relative performance, the relative performance function. So we're trying to spot what is the drop in the performance. So we're trying to get for every time step this vertical drop in performance. And this is how we reconstruct for a given accident happening on a link. We're trying to capture the spatial temporal impact and trying to find for every time step how much the network dropped in performance. So this is for the single collision. So we did it for every single collision happening in the network. And so for instance, for the same link that is subject to many accidents, we did an average in order to determine the vulnerability of this link, the resilience of this link. Okay. So this is an example that also shows how we're doing this analysis. So we have an accident reported to happen on a given link in downtown Calgary. And then you can see how the congestion is building up, and then how it's shrinking. And again, these are the reported collisions time. So 5:15, and then the clearance time reported. Yeah, this is reported, and this is the reported. And so we construct the area is the resilience matrix. So this is the resilience of this link. And then if we have different accidents all happening on the same link, we take the number of accidents and we take this area and we divide it by the number of accidents. And then we rank that and do a clustering in order to get the resilience loss. So the ones that are in red are the most, the ones that are have low resilience. And so I'm mainly spotting the one that have, the red ones that have low resilience. So we identified, so we did that for all collisions happening in the network. So we spotted that the western entrance of downtown has low resilience. But again, we don't know why we have low resilience. Is it because of the vulnerability of the links, or is it because of the slow response time? So we did the analysis again, and we can spot here. So this is the recovery time analysis, and this is the vulnerability analysis. So we can see these links that were shown to be low resilient is mainly due to the low response time, not to vulnerability of the links. Okay. So this is the final one that I'm going to present. It's more related to congestion propagation prediction model. So again, there are lots of studies on recurrent congestion prediction, but mainly on freeways and on arterials. Very few studies are related to non-recurrent congestion and to urban network, because it's much more challenging to do. And this is what we're trying to do here. So one of the applications of this study is that often when you have a collision and you look at the navigation system, the navigation system provides information related to instantaneous delays, so the delays that are occurring right now. And sometimes the vehicles, when it's traveling to reach its destination, it might even get stuck in traffic before a rerouting is being issued. So if your guidance system provides predictive information, so that provides the guidance based on predicted travel time, that would have saved the some delays. So we use the same database, but also we found that, especially for Calgary, because it's a cold city and we have snowstorms, I don't know, like we have snow like almost 6 months during the year. So we found that by augmenting the data with weather condition, we also improved the accuracy of our model. So basically we have, again, 2 steps, one speed forecasting step and one congestion quantification step. So here we're building a deep learning approach in order to predict the travel time over the next period, and then taking that as input and comparing it with the typical travel time and change in travel time, we build our congestion index. So in this way, we're also capturing when the impact is taking place, how much it's going to take long in order for the congestion to dissipate, and also the spatial impact. So this is we use a graph convolution network with long short-term memory, and it has 2 components, a spatial learning component and a temporal learning component. The spatial learning component, it looks at the connectivity, the network connectivity, and also gets information from the speed database in order to find the links that are affected, also using some hypothesis testing. And the temporal learning, it's basically a time series analysis in order to predict what are going to be the speeds in the next time interval. And so we augmented also the data with weather data, because we found that it really improved the accuracy of our network prediction. And so this is an example of one collision happening again on macro terrain. And we're basically looking at the speed being predicted on these links. So we found that the mean absolute error is reasonable, so the model is able to reasonably predict the congestion and the speeds. And so when we did that for all the collisions in downtown, we got a mean absolute error of 2.98. And this is pretty good because for non-recurrent congestion, most model MAE is between 2.8 and 4.86. So now we did the second step, which is related to congestion quantification problem. So most of the time when we do congestion index, most of the index is a 0-1 index. Either the link is congested or not congested. It doesn't have a index that quantifies how much the link is congested or not. So what also the congestion effect mainly looks at the speed and how much we have dropped in speed. What is really important to look at also to change in speed, because we're not trying to only spot congestion, we want to spot congestion during caused by collision. So we want to look at the typical speed when we don't have collision and see how much percentage, how much change in speed you have for the same day of the week, same time period, compared to the one that you have when you have collision. And also so this is the congestion value. It looks at the cumulative impact of congestion and from previous steps and the actual impact of congestion. And this congestion value is compared with the congestion value for the lower bound, so the lower speed that you can obtain of the usual when you don't have collisions. So this is an example again for the same link that were subject to collision, and you can see this is the index. So whenever you have the index more than 0, this means you have congestion. And this is the lower bound, the green is the lower bound of the speed when when you don't have collision, and the red one is the one when you have collision, or the predicted one. So this is the predicted one. And so you can see like which links is affected more. So you can see the level of the impact of your collision, and also which link is more affected than the other. So this is in summary what we have done with the data that we had. And conducting resilience and predictive analytics and vulnerability analysis is going to be like more and more important in the future, especially because in the future we won't be dealing only with the transportation network. We have the communication network for connected and automated vehicles, and you have the electric grid. So the performance of our network will be really deeply entangled with the performance of these networks. So it's very important to conduct in the future this type, and this is what we are trying to do. So these are the graduate students who were involved in this research, and some of this research was also conducted in collaboration with Dr. William Lam from Hong Kong PolyU, and another PhD student also helped, Mustafa Sari. And this is the funding from this project. Thank you. I just want to add that we're going to have a new professor. We're going to hire a new professor, and the job posting is going to be soon, maybe in 1 month, in behavioral modeling. So I encourage people who are interested in doing postdoc or at the end of their PhD to apply. Thank you.
Okay, tough questions. No?
So, about the resiliency of the lines, did you consider any kind of external factors that affect this resiliency, like weather conditions or infrastructure?
Yeah, so this is why it's so important to use data, because most of the time when you do mathematical model or simulation model, what they do, they remove one link, so it's mainly connectivity analysis. They remove one link, but like sometimes a link is vulnerable because very poor, I don't know, like something going on in this network, like maybe poor geometry, poor traffic signal. So we don't know what are the cause of low vulnerability, but this type of analysis can spot the links that are have low vulnerability or low resilience, and maybe we can conduct more analysis to understand why they are. Yeah. But like you cannot do that because we just it's like as if you're looking at an observation and you're trying to reconstruct what happened in order as if you have a crime scene and you try to understand what's going on.
I can warm up the crowd with a question. It's not really a question, I'm just kind of thinking what's going on here. Does the analysis surprise you in any way? I'm thinking if we apply what you talked about today to downtown here, what would be the usual suspects?
No,
I can guess, for instance, I'll say, okay, Spadina, University Avenue, like the usual suspects. So, did your analysis surprise you, so like identifying, for instance, a link or a few links that you didn't expect that you would be?
I think most of the time, like it was, like somehow the analysis were and the results were in line with the some of the findings of other studies, but not doing data-driven analytics. So, for instance, when you have a grid network and everything is one way, so you have low redundancy in your network. So you expect to have lower vulnerability, like your network to be more and the links to be more vulnerable. But I think we spotted some links that were close to like some very high traffic generator, and you have this very high demand. So this is something that you cannot do with the simulation or mathematical modeling. So also the demand and the fluctuation of the demand is very important.
Yeah, I wanted to pick up on that because I was thinking that is it just link level or do you find like hotspots?
Yeah, hotspots.
Right? Whereby
It's a cluster. So if you see most of the results are cluster of vulnerable links.
yeah. And is that because like one link is affecting, they're all correlated, or is it because of the presence of, I don't know, if you come here to the
Yeah.
hospitals, for example, you have huge demand.
Yeah, so I think demand is very important, especially if you have, like very high fluctuation in your demand. But also because everything, like you have a connected network, you have a grid network. So this is why the impact is not on the link itself, it's an area impact most of the time. I mean, it makes sense, like it's not going to be one link.
I've had the chance to check like multiple events or multiple these events.
Yeah, so this is like something it's very difficult to do because most of the time you have one accident because of an accident that happened before. But we looked at only at single accident because whenever you have, it's become much more complex to do that. We can no more do it with this type of analysis.
And you may have mentioned it, I missed it, do you have also a roadwork construction?
Yeah. So we also included construction. Yeah. So incident means collision and also lane blockage due to construction. So we look also at construction. But it's different because it's a planned one, right? Like, I mean.
Right.
So a bit of a futuristic question. Like after identifying those resilient and non-resilient or like less more vulnerable links, what could you recommend for the city to do to like help?
Yeah. So for instance, like when we did the analysis, trying to differentiate why we have low resilience, is it because of low response time? We found, like for instance, especially the western end of downtown, we have very low response. So we need to detect the accident much more fast and also remove the accidents much faster. So and maybe like also one of the recommendations, and this is the study we wanted to do, is to do location allocation for emergency vehicles, and try to see based on this analysis to find like maybe we should place like more emergency and police cars closer to these areas, to these clusters.
To the vulnerable.
Yeah.
Related to that question, in terms of improving resiliency, is the priority more of improving the response time or making the events less impactful when they happen? Or
Yeah.
is it a bit of both?
So I think the answer is different for each link because the problem might be slow recovery time, or the problem might be vulnerable link. So if it's slow recovery time, you want to improve the detection and the removal and the fast response time. But if it's a vulnerability problem, you want to look at the link and try to find why it's like so low, exhibiting low vulnerability, and try to do like more analysis to understand. Maybe you need to improve the signal timing, or maybe you need to divert traffic around it, or if you have like high demand or so on. So it's the answer is going to be different for different things.
That was my next question. Have you thought about control actions to fix the problem? This
Yeah.
reveals the problem.
Yes, yeah. So, I mean, this is like what the student wanted to do at the next step, like location allocation for emergency vehicles based on this analysis. And we tried to talk with emergency, Calgary Emergency Center, and they're very interested to do that. So if he doesn't find a job, he will do a research assistant with me and will continue.
I'm more thinking about like things like adaptive control. You said maybe the signal is poorly designed or the routing is limited. Or...
Yeah, we didn't do this analysis. So you mean like not from the intervention related to response time, maybe like design, changing the control or change. Yeah. We didn't dig more, but like for sure that would be very interesting research.
What do you think about using simulation data to do non-recurrent congestion prediction?
Because most of the time when you do simulation data, like most of the time, you just like, you don't understand what, it's just a connectivity problem. You're just cutting a link and trying to understand what's going on. But here, you're seeing how the network is responding and how the network is absorbing. So it's a little bit, it's different, like there's a difference between simulation and observation. This is more trying to reconstruct what's going on. So it's more, I would say, real, more observed, like, you know what I mean? Like,
Yeah.
Question like
Because you have a rich data set, have you modeled the propagation speed? Like for example,
no.
no?
Yeah, you're giving me some ideas. But like, you can see, right? So if you go to the,
And because you have this spatial temporal data, so probably
yeah, so if you look here, so this is the speed of the propagation and this is the shrinkage. So we can get sugar. So we can do it, but we didn't do it. Yeah, and so this is for only one accident, but you can do it.
Lina, you mentioned in passing at the beginning that information may create a paradoxical behavior in the network.
Yeah.
Have you encountered anything like that in real data?
No, because we don't have any, I mean, Google is the only navigation device people are using today, but we don't have any access to
There's
routing
some
information.
accusations out there that, for instance, Waze is hurting networks more than helping them. I'm wondering if you've seen any evidence.
So the information paradox is sometimes you give more information and you make the network worse, which makes sense, right? Because stochasticity is good because you can distribute traffic. You have when you give people perfect information and you give them the information at this time, everybody will shift to the less crowded route. So the more information you give and the more perfect information you give, you're deteriorating your network. So if you give more...
Racist paradox, for instance.
No, this
where-
information paradox is the same as race paradox. It's the same,
Yeah.
exactly.
So you give perfect information for people to reroute through a vulnerable link, for instance. Initially, it looks good, but once you get into it, then you're stuck for a long
Right,
time.
yeah, right. So this is why it's an information paradox. So you're making your performance of the network deteriorate because you're giving them information.
But you haven't seen that in this your system.
No.
Okay, one last question, maybe? Okay, if not, I thank you, Lina, very much, and welcome back.